Swayam Prabha. Digital India. Educated India.
Yeah, welcome back. So, we are discussing about pipelining and then parallel processing for low power applications. Continuing with the thing. So, because we need for parallel processing, the data has to be fed in parallel. So, from sequential, how we will be converting into parallel, we will see in this figure. That is what we say is critical path has remained unchanged in these cases, but the interaction period is going to be reduced in this. So, what we say is x of n is the input, then if we consider in this case, as we are seeing, we will be considering 4 parallel lines. So, that it will give you a flavor of how 2 parallel lines we have to take it, how 3, and then now we will see 4 parallel units if we consider, then what is the thing is going to happen. So, the sample period what we will do is we will subsample it to t by 4 in this case. Then we will go for serial to parallel converter, and then we will be getting x of 4k plus 3, x of 4k plus 2, x of 4k plus 1 and x of k in this case. And then in this case the clock period is going to be t for multiple input and multiple output system, and output all the 4 of them will be coming out parallelly. And then we have to convert back this parallel into serial converter. So, how we can incorporate that? So, in this way clock period is going to be t by 4, and we will convert back this parallel into serial. So, which will be coming out from the circuit as y of n in serial mode. So, we will see using the switches how serial to parallel converter and then parallel to serial converter is going to work. So, this is my x of n, and then input is t by 4. So, we will provide the delay element in our path, and we will be providing the switches basically to see that all the output whatever input has been given, output will have 4 of them. So, every t by 4 clock cycle, so you will be switching on one of the unit. So, all the 4 inputs are ready after my t by t clock cycle. So, then what will be this is how we will be feeding in all the 4 parallelly. Now, this parallel has to be converted into serial basically. What we are going to do, output what we have it is y of 4k plus 3 plus 2 and then plus 1 and then 4k. So, what we have is this is going to operate at 4k, this switch, and then you will be closing them every t by 4 as you are seeing it in this. Y of n is the input, and one of them is going to be opened, and then you will be sending after a delay. So, for the first this thing switching, all of them will be switched parallelly. So, you will be taking all the 4 inputs. So, this will have a 0 initially what you will be putting it, and then you will be switching on this, and then you will be seeing that 0 is going to be percolated first, and then you will be operating on one after the other. 4k will be coming out first, and then next this one after 1 unit of time, and then next this one. So, each one is clocked at t by 4. So, in a 1 clock cycle, in the 4 clock cycle, so you will be getting 4 outputs. This is how we will be doing the serial and parallel conversion and then parallel to serial conversion. So, what happens, why parallel processing is required? So, parallel leads to duplicating many copies of hardware, and the cost is going to increase, as well as if we are operating with same units or same voltage, we know that our speed is going to be increased and power consumption is going to be more. So, then why use this? So, we say answer lies in the fact that the fundamental limit to the pipelining is at I/O bottlenecks. So, that is referred to as communication bound, composed of I/O pad delay and the wire delay. So, in this case you know chip 1 and chip 2 is there. This is the between the two chips, this is the communication delay what we are going to have it. So, in the case of pipelining, if my communication cost is more than pipelining, then no point in going for the pipelining stages, number of stages to be increased. Then it is better to switch over to parallel processing. Then I can work on independent data in these cases. So, what we call it as this is the parallel transmission what I can have it. So, you will be seeing that T is my computation. So, taking in the data from chip 2 to here and data going from chip 1 to chip 2. So, this defines the thing. So, we will see that how we can combine our fine grain pipelining and then parallel processing. So, you will be seeing the iteration. We said that sample period is equal to T sample in this case. Then what happens if I put both of them pipelining and then parallelism, it becomes 1 by Lm into T clock. So, that means to say 1 by 6th of Tm plus 2a it is going to be at iteration every iteration I will be getting 1/6 of my what is it, I have increased my clock speed. How I can do this fine grained parallelism? So, you will be seeing that input is x of 3k plus 2. So, x of 3k plus 1 and x of 3k. So, this is our parallel unit, and then when I come to multiplier, I can bifurcate them into pipeline mode, that is M1 becomes 6 clock units and the other one I can take it as 4 clock units. So, I have provided two pipelining basically, M is equal to 2 and L is equal to 3, then my iteration time, that is how it is going to be, 1 by Lm is 1 by 6 of that original time. What it will be, I will be getting the output. So, you will be saying just all the multipliers we have made it as pipeline multipliers. So, that multiply clock time is made equal to the other side of the leg what we considered in the previous example. So, what is the underlying low power concept we have to look in? We said by I can increase 6 times the clock speed for my both the pipelining and parallelism, or at the clock rate 1/6 of it what I can operate, but how we are going to have a power low power getting the thing. So, initially we said that this is the propagation delay equation what we had it. So, the time period you will be seeing that for the sequential power consumption we call it as C total V naught square into F into T sequential is our clock period what we will be taking for every bit of data. So, then what happens, our delay is given by propagation delay PD is given by C into charge, basically my capacitor charging time, and then V naught what is the power input power, and then K is a constant because this is proportional to, we are assuming the K, and V naught is our input voltage and Vt is the threshold. We know that in CMOS circuit, so we have a threshold unit. So, in NMOS we will be seeing that 1.5 volts, whereas in CMOS it is going to be 0.5 volts, above that we consider it as 1 volt. So, that way we will see that power consumption is given by P is equal to C total into V naught square into F. Okay. So, for the sequential filter when I apply this, this is what I will be getting it, and then when I put the propagation delay is substituted, I will be getting C charge into V naught divided by K into V naught minus Vt whole squared. So, we are substituting V naught with this, and then into f, so which is going to be 1 by time for sequential. So, when I do the pipelining, what is the thing is going to happen? We say it is m level pipeline system, the critical path we say is 1 by m. So, that is capacitance to be charged in a single clock cycle becomes 1 by m. So, as you are seeing in the sequential, I have to charge this capacitor in T sequential, whereas in the pipeline if I assume m is equal to 3, then the capacitor has to be charged, as you will be seeing the time is going to be reduced. Basically we call that as beta into V naught. So, here initially it was V naught and we will assume beta into V naught. The clock frequency is, if we maintain the same clock frequency and we say the power supply can be reduced to beta times V naught. We say it is 0 is less than or equal to beta, which is less than 1, 0 is less than beta, which is less than 1. So, coming to low power continuation, we say power consumption, what we said for the pipelining, it is going to be C total into beta squared into V naught squared into the frequency. So, which we apply it as a sequential thing, which is beta squared into P sequential. Then what happens to our propagation delay? So, that is T sequential, we will be having C charge into V naught divided by K into V naught minus V t whole squared, and for the pipeline case we said the charging unit is reduced by m, whatever in this case we have taken it as 3. So, otherwise in normal C charged by m, what it has to be charged to the in pipelining into beta into V naught, we are substituting V naught with beta into V naught, and here also we will be substituting K into beta into V naught minus V t whole squared. Then we will apply that sequential is equal to period of pipelining stage. If we substitute them, then what happens? By simplifying it, you will be getting it m into beta into V naught minus V t whole squared. So, which is equivalent to b into V naught minus V t whole square. From this equation we will be getting our beta. So, we will consider an example here. So, we will consider a 3-tap FIR filter and its fine grain pipeline version, what we will be assuming it. So, it is shown in the following figure that this is the original or 3-tap FIR filter and this is our fine grain parallelism what we have considered. So, in this case what the parameters have been given is my multiplier unit is going to take 10 units of time and my adder will be taking 2 units of time, and you have been given the threshold voltage is given as 0.6 volts and then V naught, that is the supply voltage, it is operating at 5 volts and the capacitor of multiplier is equivalent to 5 times that of the capacitor of the adder. So, you will be seeing that pipeline filter, the multiplier is broken into 2 parts, M1 and then M2 with computation time of 6 units and then 4 units, which will be totally accounting for 10 unit of time with capacitance of 3 times and 2 times that of an adder respectively, what we will be considering it. So, what happens to the our equation? So, original what we had was C charge was given by Cm plus Ca. So, we said Cm is 5 times of Ca, which is going to be 6 times Ca. In the fine grain it is going to be C charge equal to Cm1, which is equal to Cm2 plus Ca, because we have one pipeline stage there. So, which is equal to 3 times that of Ca, what it is going to be. So, then our equation we will be seeing that m is equal to 2 in this case we have assumed, and then supply voltage V naught is 5 times beta minus V t is 0.6 threshold, which is whole squared is equal to which is equal to beta into 6 is our Ca basically minus 0.6 whole squared. So, which comes there are, as when you solve this equation. So, it is going to be beta will be equal to 0.6033 or 0.0239. So, we say that because our threshold voltage is 0.6 voltage what it has been given, this value is much below that threshold. So, capacitor will not be switching on. So, we say that this is infeasible. So, it becomes 0.6033 is the supply voltage what we can reduce to, that is a ratio is we call it as beta squared. When I take it, the reduction is going to be 36.4%, but we say that pipelining should have given me 50%, but in this case only the reduction can be 36.4%. So, as you can see in this case, when we do the comparison, how it is going to be, that is system is power is reference and sequential FIR original if I take it, that is in terms of my power reference, and pipeline FIR without reducing the V naught, what I will be getting is 2 times the original one I am supposed to get the output. And then in case of with reduction in the voltage, so it becomes 0.364 times the whatever power consumed with respect to reference. And the clock period unit time what we are assuming is, here it is going to take 12 units of time in the original, because multiplier is 10 units and then adder is 2 units which is 12, and then in the case of pipeline, so it will be taking 6 unit of time, whereas when I without reducing the voltage, but if we reduce the voltage, so we know that the clock period remains as the original one which will be having 12 units of time, and sample period we know that this is 12 units and here it becomes 6 units, whereas in the pipeline with reducing power it will be still 12 units. So, we will see that parallel processing for low power how we are going to achieve it. So, we say that we have L parallel system. Since maintaining the same sample rate, clock period is increased to L times the sequential one. So, this means that your C charge is charged in L into T sequential and the power supply can be reduced to beta times V naught. So, we are seeing that in the sequential the capacitor that is going to be charged with respect to T sequential at V naught voltage, whereas in the parallel if we are assuming L is equal to 3. So, then what happens, this becomes 3 times T sequential all of them, and power the voltage reduction is going to be beta into V naught what we will consider. So, we will same thing what we will be applying the equation. So, the parallel will be L into C total into B into beta into V naught whole squared plus our frequency by L, because I will be getting 3 outputs in one clock cycle. So, I will be my frequency can be F by L. So, which we will be equating it as beta squared into P sequential. Then what happens to our propagation delay? So, this is T sequential original C charge into V naught by this one. In the parallel case, C charge into beta into V naught whole divided by K into beta into V naught minus V t whole squared. So, then L into T sequential is equal to T parallel. So, we will be applying both together L into beta into V naught minus V t whole squared, which is equal to beta into or V naught minus V t whole squared. So, we will be getting a beta from this equation. As an example, we consider a 4-tap FIR filter shown in this figure basically, and we have going to consider 2 parallel versions of this one. Here we will be considering the first version, in the next slide we will consider the second version. What is the thing is going to happen, we will see that. The 2 architectures are operated the sample period 9 unit of time. Assume your multiplier is going to take 8 units of time and adder is going to take 1 unit of time, and the threshold in this case voltage is given as 0.45 volts. above that capacitor is going to be charged to 1. So, V naught is equal to 3.3 volts what it is given, that is supply voltage, and then Cm what we are going to have is capacitor for the multiplier is equivalent to 8 times that of the adder. So, it is asking, the question is what is the supply voltage of the 2 parallel filter and what is the power consumption of the 2 parallel filter as a percentage of the original filter. So, you are seeing the 2 parallel filter what we have considered. So, here in this case what is it, original capacitor charge is equal to Cm plus Ca, and then in the case of 2 parallel section what happens, Cm plus 2 Ca, which is nothing but 10 times Ca, and then if we apply the equation, so we will be seeing that 9 times 3.3 into beta minus 0.45 whole squared, which is equal to 5 times beta into 3.3 minus 0.45 is the threshold voltage whole squared. So, in this case beta becomes 0.6589 or 0.0282. As previous case we have to ignore this because this is less than the threshold voltage of 0.45. So, we will be considering 0.6589 as beta, then for the parallel section 0.6589 into 3.3 volts, which is going to come down to 2.1743 voltage. So, how much reduction we were able to get it? 43.41% in this case. So, coming to the next section, that is parallel, here what we have done is you have the 4 multipliers here and here also 4 multipliers, and you will be seeing that x of 2k and x of 2k plus 1 are the input to this structure. So, we will see that by modifying it the structure in this way, what we have taken is x of 2k here with little arrangement, that is we call it as a linear phase FIR filter. If I consider the thing, H naught and H2 can be here, and then the other thing I can derive from that, that is H naught plus H1 will be multiplied here, and the other one is H2 plus H3 what I can combine, and H1 and then H3 are coming from this parallel section. So, by doing little modification to the previous structure, what we will be getting is output is going to remain y2 of k and y2 of k plus 1. So, one of the assignment for you is what will be the output at here junction A and then junction B, what you have to calculate as well as at C. So, we call this as area efficient 2 parallel multiplier. So, you have to count how many adders and how many multipliers are present in this case. So, we assume that we are charge is Cm plus Ca, what we are assuming it, which is going to be 9 times Ca, because 8 Cm plus 1 Ca is equal to 9 Ca, and we have new 2 parallel, that is charge of the capacitor is equal to Cm plus 4 times Ca, what we will be having it, because we have 2 parallel section. So, which is equivalent to 12 times your original adder capacitor. So, if we substitute in this, because here also it is 2 parallel section, 2 into 9 we will be achieving this equivalent to 12 times beta into 3.3 minus 0.45 whole squared. So, then beta turns out to be 0.745 or 0.025. So, as earlier cases this is infeasible, and we consider our pipeline the parallel version of it is going to have 2.45857 volts, and then the ratio with respect to this you will be calculating it as 43.6% the saving in the voltage. So, in the previous case you have saved 43.41, here you are saving 43.6 100% with area efficient, because I have reduced my adjacent multiplies by introducing the delay in a proper. So, please look into this. So, now can we combine pipelining and then parallelism together and then try to achieve better voltage reduction? That is what we will look in this slides. What is it? We have the sequential as usual, and then pipelining we have C charge divided by M, whereas in the case of our parallel it becomes L time T sequential. So, which implies that I will be making the left hand side as number of stages for pipeline into number of stages for parallelism, which is given by M and L, into beta into V naught minus V t whole squared, which is equal to this. So, if we consider both of them, M is equal to L is equal to 2, then we are operating V naught at 5 volts, then what threshold is given as 0.6 volts. So, if we compute the values, beta becomes 0.4, then beta squared will be 0.16. So, this is how we will be doing the thing. This is our sequential. So, what we have done is 3 parallel units what we are going to have it. So, and then one pipeline what we have considered. So, to conclude this pipelining for low power, we discussed about 3 tap FIR filter for pipelining, and then we consider for parallel processing also 3 tap and then 4 tap and 2 tap filters, and then pipelining and parallel processing together, how you can achieve low power. That is what would demonstrated. You can work out some of the problems and then see that how it is going to improve on your power consumption, that is what it is going to be reduced. So, in the next class we will be discussing about IR filters, that is low pass, and a little bit on high pass filter. And then as we know that IR filter is going to lack in the case of linear phase, we will be achieving only in FIR filter. So, IR filter becomes non-linear. So, we will look into that in the next class. Thank you.